Hello, my name is Jingyi Li, and I'm presenting our paper on the benefits of image-schematic metaphors when designing mixed reality systems on behalf of my co-author, Ola Kristensson from University of Cambridge. So, what exactly is an image-schematic metaphor? We'll simply refer to it as ISM from this point. Evidence in child development research suggests that as an infant, we learn a set of these basic concepts, also known as image schemas, from our everyday bodily experiences. One example is front and back, which is usually the side with the face in humans and the side opposite. Another example is path, an image schema formed when we repeatedly see objects moving along a trajectory in space. These image schemas become the fundamental building blocks of the human conceptual system and are used to understand other new concepts that are more complex and abstract. For example, we use image schema front and back to understand abstract concepts future and past. I believe all of us share the experience of walking on a street when locations in front of us will be reached in the future and the locations at the back has been reached in the past. The repeated co-activations between abstract concept future and past and image schemas front and back lead to a permanent and robust ISM. Future is front, past is back. There are many of these robust ISMs grounded in universal sensory motor experiences, and they should be universally shared among individuals. For any specific knowledge domain or design context, it is possible to identify such ISMs from people's spoken language and interaction behaviors. For example, when someone says he is near and dear to her, it reflects an ISM, emotional intimacy is closeness. And when people interact with brighter buttons and text boxes while ignoring the darker ones, it indicates an ISM, capability of action is brightness. When embedded in interactive systems, ISMs can aid users' cognitive processes through embodied metaphorical understanding, using fundamental embodied experience to understand new concepts. Prior studies have integrated ISMs into screen-based graphical user interfaces and embodied interactions, and evaluated the benefits through empirical comparisons. Compared to other types of interaction techniques, mixed reality offers the strongest forms of embodiment, which naturally lends itself to the effective implementations of ISMs. And this could amplify the power of embodied metaphorical understanding beyond what is known to be possible with screen-based systems. This motivates our exploration on the benefits of integrating ISMs into different aspects of an MR system. The context we chose for our exploration is MR instruction authoring. One challenge for line workers is that referring to paper-based or video-based instructions requires constant switch of attention between the instruction and the work context. MR instruction effectively addresses this challenge by directly overlaying virtual instructions into the real-world context. However, transforming a video instruction to an MR instruction can be challenging as it requires programming and graphical expertise, and there are very few tools supporting non-experts, for instance, a line manager, in authoring virtual instructions in mixed reality. One of these MR instruction authoring systems is a Microsoft solution, Dynamic 365 Guides, based on which our baseline was implemented. Using the baseline system, users can translate an existing video tutorial for assembling a model to an MR tutorial by creating modifying virtual assembly parts, and place the virtual part at the correct real-world location for each step, using a HoloLens 2. We hypothesized that redesigning the baseline by integrating a set of ISMs into different system components can lead to better task performance and learnability. The ISMs used to enhance the baseline were identified in one of our previous papers, which discovered a set of ISMs shared by both younger and older adults in the domain of technology learning. Among all these ISMs, we found that the baseline was not congruent with 12 of them. We redesigned the baseline system following a system component ISM instantiations design pathway. Firstly, we listed 6 functional components that made up the baseline system. Then, for each system component, we associated with relevant ISMs. For each ISM, we associated with one or more design aspects of the MR system where it could be instantiated. We'll now take a look at the ISM-informed redesign of each system component. The baseline uses a standard video player where users can drag and move the slider thumb to go back and forth in the video. We redesigned the visual appearance and interaction of the video player using these 3 ISMs. The video playback slider was visually redesigned to be a path-like sprite sheet consisting of multiple smaller images that corresponded to each assembly step of the video tutorial. Users can click on any image on the sprite sheet slider to pause the video at the corresponding assembly step. The step card in the baseline system consists of a Go Back button, a Go Next button, and a text indication of the current step. Based on 4 relevant ISMs, we redesigned the visual appearance of the step card to be a segmented path and spatially align it directly underneath the video playback slider to enable spatial correspondence. In the baseline, the toolkit menu is always visible and fixed at the bottom right of the user's field of view. Based on 5 relevant ISMs, we redesigned the spatial placement and interaction of the toolkit menu. The ISM-enhanced toolkit menu is attached to the user's left palm. Whenever a user needs the toolkit menu, they hold up their left hand and the menu would appear close up and right in front of the user. When not in use, the menu would be hidden when the user put down their left hand. We also redesigned the baseline's instruction display style from text instruction to 3D semi-transparent hand animations that demonstrate interaction. In the baseline, there is no audio feedback when users manipulate virtual objects. A relevant ISM, the form of operation is path, suggests that a manipulation behavior is a path that consists of a starting point and an end point. We integrated this ISM audibly by implementing a starting sound and an ending sound signaling the start and end of every interaction behavior. To select a button in the baseline, users hold their hand rate on the button for a short period of time until it gets selected. A relevant ISM suggests that users force the system to function by pressing a button. We redesigned all hand dwell buttons to be pressable buttons. When pressed, the front plate of the button retracted in response to the interaction, offering a visual representation of the image schema composition. Now we have a baseline system and an ISM-enhanced version of it. We carried out a between-subject user study with 16 participants using the baseline and another 16 participants using the ISM-enhanced system to complete the same task, which was authoring assembly instructions for a 12-part Lego model in MR on a HoloLens 2. The study started with a 5-block training phase, followed by the formal 12-block test phase. Now let's take a look at the results. Participants using the ISM-enhanced system completed the same task significantly faster than those in the baseline condition. And when we rank all participants by performance in both conditions, we found that at every ranking position, participants in the ISM condition was consistently faster than their counterpart using the baseline. When looking at error rate, we did not observe any significant differences between the two conditions. However, at every performance ranking position, participants using the ISM-enhanced system consistently had the same or lower error rate compared to their counterpart using the baseline. Moreover, we computed the learning curves during the 5-step training session for both conditions and computed the learning rate based on the best fitting curve. The ISM condition had a higher learning rate compared to the baseline. Looking at individual participants' data, we found that participants in the ISM condition showed significantly greater learning rate and learning gain, which is measured by the completion time difference between the last and the first block. Results also suggest that the ISM-enhanced system enabled higher mental efficiency. In our samples, NASA TLX ratings revealed no significant differences in terms of subjective mental load, while the ISM system enabled significantly better performance. This indicated a higher mental efficiency in the ISM condition. Detailed calculations and analysis of mental efficiency can be found in our paper. Moreover, user experience questionnaire ratings indicated that the ISM-enhanced system was perceived to be significantly more perspicuous, efficient, and novel, and are equally attractive, dependable, and stimulating compared to the baseline. So, what exactly are these results telling us? One of the most important findings of this work is that we quantitatively observed a significant enhancement in learning rate and learning gain enabled by the integration of ISMs in interactive systems. Such enhancement could be attributed to the successful activation of embedded ISMs when users encounter new concepts during the initial interactions with the system, which facilitated the comprehension of system functions and behaviors. This minimized the mental load associated with learning to navigate a system, so users had more cognitive resources available for handling the task at hand, leading to higher mental efficiency and better task performance. Interestingly, performance benefits were observed through participants with varying performance levels, from top performers to those facing the most challenges. This indicates that ISMs could be the ingredient that everyone can benefit from, whether you're a seasoned pro in MR interaction or a complete beginner. Taken together, ISMs offers a promising method for creating easy-to-learn and use interfaces and interactions in MR systems that resonate with the mental models of a wide range of users without the need of costly adaptations. However, it is more than important to recognize that these benefits were observed in just one possible implementation of ISMs, and are not generalizable without further comparative studies across different tasks and designers, while also considering different forms of user interfaces and mixed reality. To facilitate such investigations in the future, this study uniquely demonstrated an ISM-inspired design pathway, which can assist designers to systematically integrate a set of ISMs into different aspects of an MR system. This is the first attempt to operationalize ISMs as a practical design method in mixed reality, and future studies can easily customize or augment this basic pathway based on specific requirements of various design tasks and different forms of user interfaces, exploring ISM's wider applicability in the design of MR systems. Thank you for listening to this video presentation.